Okay, let's look at this problem. We have a gas in this piston cylinder device. The piston has a mass of 4 kilograms and a cross-sectional area of 35 centimeters square, and there is a compressed spring above the piston. If the atmospheric pressure is 95 kilopascal, determine the pressure inside the cylinder. Okay, so the first assumption is that to determine the pressure inside the cylinder, we need to assume that this piston does not move. Okay? When the piston does not move, what does it mean in terms of force? If you look at this piston, there should be atmospheric pressure and the pressure by the gas inside the piston cylinder device and spring, etc. And when you combine all the forces acting on the piston, the net force should be 0. If the net force is this way, then the piston is going to move upward. If the net force is this way, the piston is going to move downward. Okay? So our assumption is the piston does not move. In that assumption, we can make a free body diagram. So this is the piston, and we can analyze all the forces acting on this piston. So what kind of forces are there? First, we can think about the pressure by this gas inside the cylinder. So there is a pressure by the gas acting on the bottom surface of this piston. The pressure value is unknown, so this P is what we want to determine. What else? What kind of forces are acting on this piston other than this pressure by the gas? Spring, yes. So there is a spring force in what direction? This way? Down, down, because it is compressed. So there is a spring force acting on this way. I'm going to say F force by spring. Anything else? Weight, yes. So there's a weight of the piston this way, the gravity direction, this way. And how do you determine the weight? It says 4 kilograms. So if I say the weight of the piston is 4 kilograms, is that right? No. What is 4 kilograms? The mass of the piston. Mass is not a force. So if you want to determine the force by this mass, you need to multiply by what? Force is mass times acceleration. What kind of acceleration here? Gravity, right. So it's going to be mass times gravity, 9.8 meter per second square. So mg is the weight. Is that it, or there is anything else? There's one more. Yeah, the area. So what is acting on here? Yes, the atmospheric pressure. The atmospheric pressure is acting on the top surface of this piston. That is PATM. Then we can determine the net force acting on this piston. If you want to determine the net force, you need to decide what is the positive direction, what is the negative direction. So we can say either upward is positive or downward is positive. Which one is right? Either, so you just need to pick one. So if you pick upward is positive, so let's calculate the net force. The sum of all the forces acting on this piston, assuming upward direction is positive. And what do we have? First, this pressure by the gas, the unknown P. So I can write unknown P here. And what is the direction? Positive direction, right? And what else? Atmospheric pressure. Is it a positive direction or a negative direction? Yeah, it's a negative direction. So minus TATM. And we have the weight of the piston 4 times 9.8, which is mass times gravity. And it's a negative direction, so minus mg. And we have the force by the piston spring, which is also the negative direction, so minus F of S. And what is the sum of these forces? 0. What about if the sum of these forces is 1? Then the net force is positive, so the piston should move upward. If the net force, when you calculate this one, if it is negative value, then the piston is going to move downward, okay? When the piston stays there, that means the net force is 0. And we know the atmospheric pressure is 95 kilopascal. So I'm going to say this one is 95 kilopascal, and the mass of the piston is 4 kilograms, and the gravity is 9.8 meter per second square, and the spring force is 60 newtons. So if we say 60 Newton here, then you can calculate this pressure, right or wrong? So if I solve this equation, we get the pressure by the unknown gas in the piston cylinder device. Is that right, or did I make a mistake? Yeah, I made a mistake, right? One mistake. Right, because this one is pressure. This one is force. They have different units. So you need to convert force to pressure or pressure to force. So you can only have forces or pressures, right? So how can we do that? What is the relation between pressure and force? Pressure is force divided by area. So if you want to convert this pressure into a force, you need to multiply by the area. So PA is force. So what kind of area? Any area? No, the area where pressure is acting on. So the pressure is acting on the bottom surface or the top surface. So the cross-sectional area of the piston is the area you need to multiply by. Okay? So what is it? The cross-sectional area is 35 centimeters squares, but you don't like centimeters. You prefer meters, right? How can you convert that? 1 meter is 100 centimeters. And we have a square here. 1 meter square is 10,000 centimeters square. So you need to divide this one by 10,000. Then it's going to be E times area. TATM times area. This area is 0.0035 square meter. This one is also 0.0035 square meter. So if you then you can determine this pressure. If you do, the pressure value is, do I have it? 147 kilopascal. So this completes chapter 1. Now you have a new homework assignment, which is due by a week from today. So next Thursday at 9:30, right before this classroom, okay? Any question about chapter 1? No? Okay. Chapter 2, we are going to study the first law of thermodynamics. What is the first law of thermodynamics? The conservation of energy principle, which is pretty simple to understand. So this is me. So in the morning, I was very hungry, so I ate 3 hamburgers. And in the afternoon, I was too full, so I pooped out 2 hamburgers. Then how many hamburgers in my belly? 1. That is conservation of energy principle. 3 minus 2 is 1. So that's what we are going to study in chapter number 2. But if you want to, use that conservation of energy principle, you need to quantify each hamburger, right? So how you quantify energy of a system? So that's what we are going to study. There are 2 different forms of energy that we are going to study. The first one is a macroscopic forms of energy, and the other one is microscopic forms of energy. So macroscopic forms of energy, there are 2 of them. Kinetic energy, the energy associated with velocity, and potential energy, the energy associated with gravity. I'm pretty sure that you have a good knowledge about kinetic energy and potential energy. The other energy is microscopic forms of energy, those related to the molecular structure of a system and the degree of the molecular activity. So things like thermal energy, those related to temperature change, or chemical energy, like a chemical reaction, or nuclear energy. So if you combine macroscopic forms of energy and microscopic forms of energy of your system, that becomes the total energy of the system. Okay? We use this capital U for microscopic forms of energy, in other words, internal energy, the sum of all the microscopic forms of energy, and Ke for the kinetic energy, and Pe for potential energy. Then how can we determine U? We're not going to study that here. We are going to study how to determine U later in chapter 3. This is a little complicated. Then instead, we are going to study how to determine Ke, kinetic energy, and Pe, potential energy. Kinetic energy is pretty simple. It is going to be mass times velocity square divided by 2. Mass times velocity square divided by 2. That is kinetic energy. But you remember, in chapter 1, we studied extensive energy, extensive properties, and intensive properties, and we use intensive properties in our energy balance equation. So what is the intensive property of kinetic energy? Dividing kinetic energy by mass, that is specific kinetic energy. And when you divide this kinetic energy, we usually, write the lowercase Ke to show that this is a specific energy. So Ke, that is the actual kinetic energy. If you divide this kinetic energy by mass, you get lowercase specific kinetic energy. So kinetic energy is mass times velocity square over 2. The specific kinetic energy is just velocity square over 2 without mass. Similarly, potential energy can be determined by mass times gravity times elevation z, and you can also divide this potential energy by mass. That becomes specific potential energy PE, and we can use gravity and elevation z. The unit is kilojoule per kilogram or joule per kilogram. Then how can we determine the total energy of a system? We just calculate the sum of microscopic forms of energy and macroscopic forms of energy, and they are internal energy U, kinetic energy KE, and potential energy PE. That's how we determine the total energy. U plus mass times velocity square divided by 2, mass times gravity times elevation z. But I told you that, that we prefer using intensive properties. So if you divide this total energy of a system by mass, you get this lowercase e, that is total energy of a system per unit mass, which is lowercase u, lowercase ke, lowercase pe, and it's going to be u plus v squared over 2 plus g times elevation z. So that's how we determine the total energy of a system per unit mass. Sometimes we prefer using flow rate. Instead of mass, we can use mass flow rate whenever we have a steady open system. So we will use this flow rate later in chapter 4 when we study an open system. Then when we study, the flow rate, we use mass flow rate. Mass flow rate is mass per unit time So if you divide a property by time t, we put a dot on top of this property to show that this is this property per unit time. Okay? And how can we determine this mass flow rate? By the way, the unit of this mass flow rate is going to be mass kilogram T time second. So it's going to be kilogram per second. And this mass flow rate can be determined by two different ways. The first one is density times volumetric flow rate. Because density is mass divided by volume. So from here, we have m dot, which is the same as mass divided by time. And if you multiply volume over volume, which is just 1, you can say this is going to be mass over volume and volume over time. So it becomes mass over volume times volume over time. So this one is what? density. This one is what? Volumetric flow rate, volume per time. Okay, so that's how we determine the mass flow rate. If you know volumetric flow rate, like a gallon per minute or something, that when you buy a flow meter. There's another way to determine this mass flow rate, which is density times velocity, average velocity, times cross-sectional area. That's how we can determine the mass flow rate. How? If you see this m dot, which is mass divided by time, and we can also say the same thing, mass divided by volume times volume divided by time, the same as this one. Then this volume is going to be area times distance. So mass divided by volume times distance times area divided by time. So this one becomes density. This one becomes, what is distance over time? Velocity, average velocity, times area, cross-sectional area. So this is what you see here. Okay? Then we will study this mass flow rate later when we go to chapter 4, studying steady state open system. Then let's go back to the total energy. The total energy is going to be the sum of internal energy U, kinetic energy Ke, and potential energy Te. Then what kind of internal energy are there? The first one is thermal energy, the energy associated with heat transfer, and chemical energy and nuclear energy. In thermodynamics, we neglect chemical energy or nuclear energy. And we only study thermal energy. So when we say internal energy U, it means thermal energy. Because we assume that there is no chemical reaction, there is no nuclear reaction. In most engineering processes, yes, there are no chemical reactions, there are no nuclear reactions. And there are two different thermal energies. One is sensible energy, the other one is latent energy. Sensible energy is the energy associated with temperature change. So when you heat this coffee, its temperature goes up. In other words, the sensible energy of the coffee increased due to heat transfer. But once the coffee reaches its boiling temperature, any heat transfer into the coffee is not going to increase the temperature of the coffee. Instead, it's going to evaporate coffee, right? That the energy associated with phase change from liquid to vapor or solid to liquid, or the other way, it is called latent energy. So when we say thermal energy, there are two types of thermal energy: sensible energy and latent energy. Okay? It's very important to understand whether there is latent energy change or not when you look at an engineering process, because when we go to chapter 3, trying to determine internal energy U, we use different approaches to determine this U when we only have sensible energy change and when we have both sensible energy change and latent energy change. Some examples, when we have latent energy change, it's going to be air conditioning system. We have a condensation, evaporation of refrigerant inside. That's how we pump heat from this high temperature room to the outside, or refrigerator, or the steam turbine, or the way we generate electricity. Some people say that, oh, there is a wind farm over there, so we can generate the electricity by wind. But the majority of the electricity that we use on the earth in this the states, we use steam turbine. We use what is called Rankine cycle, the generate steam, let it, the run turbine. That's how we produce electricity. So those are, some examples when we use latent energy change in our engineering process. Okay. So, however, determining this U, depending on whether it is sensible energy or latent energy, is a little complicated. So we are going to use one, chapter to understand how to determine U. That is chapter 3. So until then, in this chapter 2, we are going to focus on macroscopic forms of energy. They are potential energy and kinetic energy. Okay. So what are potential energies and kinetic energy? They are mechanical energy. When we say mechanical energy, there are 3 mechanical energy. So some people, they get confused here. So when we talk about the total energy of a system, there are 2 mechanical energy: kinetic energy and potential energy. But when we talk about mechanical energy, there is one more mechanical energy, that is flow energy. The energy associated with a flow. So when we say mechanical energy, it's not just kinetic energy and potential energy. It is flow energy, kinetic energy, and potential energy. Then you may have a question. I know what is kinetic energy. When something has a velocity, yeah, it has kinetic energy. When something, is somewhere up there, then we can say it has a high potential energy. Then what is flow energy? The easiest way to understand flow energy is, from an example. This classroom has only one door, but let's assume that there is another door, imaginary door here, okay? So that's inlet, that's exit, okay? So this is room ET 128. So this is inlet, this is exit, outlet. And because I'm too famous, many students all over the world want to come into this classroom. That's our assumption, okay? So this classroom is completely filled with students. So completely, there is no space, completely filled with students. Imagine that there are, maybe 500 students in this classroom. It's going to completely fill this room, right? So students are the system in this problem, okay? Nothing but just students. Okay, right? So it is completely filled with the students. Now there's one more students, wants to come in. So this is the entrance. There is one more students, this blue, wants to come in. Can he go in? No, it's completely field. When we talk about engineering, the system, such as your car engine or air conditioning system, refrigeration system, or turbine compressor, they are filled with a system. Can be air, water, etc. Usually completely filled, right? So if there's a new student who wants to come in, how can he comes in? Right, one has to leave. Right, that's yeah, right. But first, you need to make a space first, right? So this is the door, and it is completely filled with the students. If I want to come in, I need to push this someone standing right at the door, this way, right? To make my space and walk in. So that means that I need to provide energy into this room by pushing the students standing at the door to a side so I can, create my space, then I can walk in, right? To do so, I need to provide energy into this control volume. What kind of energy? What I just did. Yeah, mechanical energy. So how you determine that? I push it, someone, right? And that is pressure to create volume. So pressure times volume is the energy that I provided into this room so I can walk in, right? So that is pressure times volume. That is flow energy. It's simple. Then let's go back. Wait, I see something different. I thought it is pressure times volume, but I see pressure over density. Why is that? Look at the front, look at the left-hand side. Is it the total mechanical energy? When I ask like this way, then the answer is no, right? So what is it? Yeah, specific mechanical energy. What is the specific mechanical energy? The total mechanical energy divided by mass. So when you look at this flow energy, you need to divide by mass. So flow energy divided by mass. What is it? Volume divided by mass. That is specific volume, lowercase v. Pressure times lowercase v. By the way, what is specific volume? The inverse of density. So this PV can be written as P over rho. Am I right? So that's what you see here. Flow energy. It is specific flow energy. So there are three forms of mechanical energy that we can think of: flow energy, kinetic energy, and potential energy. If you divide by mass, you get specific mechanical energy. Then multiply by mass flow rate, you get the total mechanical energy per unit time. Okay. So that's everything about mechanical energy. So let's solve this problem together. At a certain location, wind is blowing steadily at 10 meters per second. Determine the mechanical energy of air per unit mass and the power generation potential of a wind turbine with 60-meter diameter blades at the location. Take the air density to be 1.25. Okay, we can do that. So what do we want to determine? We want to determine the mechanical energy of air per unit mass. So per unit mass, meaning is that specific mechanical energy. Where is the specific mechanical energy here? This one. So I'm going to write specific mechanical energy is going to be pressure divided by density and velocity square over 2, that is kinetic energy, and potential energy, gravity, elevation, c. So this is specific mechanical energy. There are flow energy, kinetic energy, and potential energy. So which energy we are going to use by this wind turbine? Flow energy, kinetic energy, or potential energy? We can determine what energy has been used by comparing the specific mechanical energy before and after this wind turbine. So assuming the air density to be 1.25 kilogram per cubic meters, that means that this density is going to be constant. What is this pressure? What kind of pressure is that for this wind? What is the pressure of this wind? The atmospheric pressure. The atmospheric pressure. That should be the atmospheric pressure. If it is not, what about if the pressure is lower than the atmospheric pressure? While you're driving, when you see wind turbine, then your car goes that way because there's a low density, right? It is at the atmospheric pressure. It's not like a black hole, right? So this one is constant. What about after this wind turbine? What happened to this density? Our assumption is that air density to be 1.25. So that is constant. What about after this wind turbine? What happened to the pressure? There any change? Goes up or down? No, it is still atmospheric pressure. So this one is also constant. So the flow energy hasn't been changed. So there's any effect on here? No, so we are not going to consider flow energy. Then what about potential energy? So after this wind turbine, the elevation Z stays the same, that's constant. Gravity is constant. So potential energy does not change, so you can neglect that. The only mechanical energy that will be affected by this wind turbine is going to be this kinetic energy. So if we want to determine the mechanical energy of air per unit mass, it's going to be the specific kinetic energy. Then how can we determine specific kinetic energy? Velocity square over 2. So what is the velocity? 10 meters per second. So it's going to be 10 square per 2. So it is 50. That is total mechanical energy per unit mass. And what is the unit? We have velocity meter per second square. So the unit is going to be meter square per second square. So that's the answer. You okay with this unit? When we say total mechanical energy per unit mass, we expect the unit of energy, joule, but there is meter square per second square. So let's check what this unit is. To check, what this unit is, we can use the dimensional homogeneity. You remember primary dimensions and secondary dimensions that we studied last week. So we are going to, to look at that. First, it's a specific energy. Specific energy means energy per unit mass. So its unit should be either kilojoule per kilogram or joule per kilogram. Right? Oops. So it's going to be either kilojoule per kilogram or joule per kilogram. Which one is what? Which one is correct? We don't know unless we check dimension of homogeneity. So let's check dimension homogeneity. So let's assume this one is right. So I'm going to check dimensional homogeneity. So kilojoule per kilogram should be the same as meter square per second square. So there are 4 primary dimensions: mass, length, meter, mass, kilogram, time, second, and temperature, Kelvin. So we have meter per second, meter per second. So these are all primary dimensions. Then what about here? We have a kilogram, but joule. Joule is not a primary dimension. It's a secondary dimension. So you can divide into 2. How do you determine this? What is the unit of this? What kind of unit is this? Energy or work, right? So how do you determine energy or work? By force times distance. Force times distance. So what is force? Newton times distance, meter. So joule is Newton times distance. We have a kilo in front. Divided by kilogram. Then let's look at that. Okay, so we found one more primary dimension, but we still have another secondary dimension. So let's look at this one. What is N? Newton. Newton is the unit of force. Force is mass times acceleration. So this Newton is going to be mass kilogram times acceleration, meter per second square. Then we have a kilo here in front. We have a meter per kilogram, meter per kilogram. So if you look at this, we can cross kilogram, kilogram, meter square. So it's going to be kilo meter square per second square. So are they the same? No, because of this kilo. So you can say meter square per second square is the same as joule per kilogram. So now you can say the answer is 50 joule per kilogram. It makes much more sense, right? Then we want to determine the power generation potential. Power generation potential means the total energy per total power possible that can be generated by this wind turbine, the total power. So we can determine total power. What is power? Power is work divided by time, or energy divided by time. So energy divided by time, what is it? Energy flow rate, E dot. So how can we determine this E dot? Energy per time. This energy can be mass times lowercase e, specific energy per time. Then this is going to be mass over time, mass flow rate, m dot, times specific energy, E. So that's how we can determine the power. Power can be determined by mass flow rate times specific energy. We already determined the specific energy. Here, specific mechanical energy is 50 joule per kilogram. So if you can find this m dot, then you can determine the power generation potential. So let's do that. How can we determine this m dot? M dot can be found by this equation. M dot is density times volumetric flow rate, or density times average velocity times cross-sectional area. So I'm going to write this one here. So M dot can be determined by two different ways. One is density times volumetric flow rate. The other one is, that's number one. Number two, density times average velocity times cross-sectional area. Then, do we know density? Yes, 1.25. Do we know the volumetric flow rate? No. Then what about this one? Do we know the average velocity? Yes, 10 meter per second. Do we know the cross-sectional area? We do not. However, we know the diameter. If you know diameter, you can determine the cross-sectional area. Pi d square over 4. So, sounds like we can use this one. So what is the density? 1.25 kilogram per cubic meters. What is the velocity? 10 meter per second. 10 meter per second. What is the cross-sectional area? Pi d is 60 meters. D square over 4. So that's how you can determine the mass flow rate. So if you calculate mass flow rate m dot is 35,340 kilogram per second. So now we have the mass flow rate and the specific mechanical energy. So if you multiply mass flow rate by specific mechanical energy, we get the power generation potential. Okay? So the power generation potential is going to be m dot times E 35340 kilogram per second times this one 50 joule per kilogram. So what do we get? 1770 kilowatt. Oh, what is watt? By the way, this watt is joule per second. Watt per time, energy per time, which is power. Any question about this problem? If I give you this problem or similar in your first exam, can you solve it? Yeah. Feel free to let me know if you have any question or if it is too fast or too slow. Okay. Any feedback is welcome. The next problem, consider a river, Chippewa River, flowing toward a lake, Michigan Lake. Is Chippewa River going to the west or east? I never thought about that. So it's going to go to the Michigan Lake or the other way, Detroit Lake? This way? Or to the bay? Okay, so the lake next to Detroit. Okay, so we have a river flowing toward the lake at an average velocity 3 meters per second at a rate of 500 cubic meters per second. So here we have a volumetric flow rate at the location 90 meters above the lake surface, determine the total mechanical energy of the river water per unit mass and the power generation potential. So the same thing, the same question. So we are going to calculate the specific mechanical energy that can be determined by flow energy, pressure over density, plus kinetic energy, velocity square over 2, plus potential energy, gravity, elevation, z. So among them, we need to determine, what will change before and after. So first, we need to determine two locations. First, the easiest way is to select on the surface. Here I'm going to say number 1, and here I'm going to say number 2. You can also say, number 1, number 2, or number 1, number 2, you can select many different locations, but you need to know these properties at each location. So the easiest is going to be when you select the surface of the river and the surface of the lake, because if you go deep, we have no idea about the pressure. If you at the surface, then you know the pressure is going to be the atmospheric pressure. So you can neglect the first term. So if you look at the pressure at the surface of the river, what is the pressure value? We don't know the value, but we know it is the atmospheric pressure. What about, the here? That is also the atmospheric pressure. Some can argue that the atmospheric pressure, the here and there should be different because there's a 90-meter difference. Technically, yes, but how much difference? Usually negligible, right? If you go to the, the 8th floor, how many floors, in the tower? The towers. Nobody knows? None of you are residents there? Okay. I've never been there. So let's assume that that's a 10th floor. So if you go to 10th floor, you need an oxygen tank? No, you don't, because the pressure decrease from the first floor to the 10th floor is negligible. But we know it's going to decrease, but negligible. Is there a penthouse in the top floor? Maybe the president lives there? I don't know. So pressure change of gas we usually neglect unless there is this much difference between Mount Pleasant on top of Mountain Everest. When I first moved to this town, I thought that it's a Mountain Pleasant. So when I got here to the the front office, and asked, we had a different the staff at the time. It was an older lady, and I asked my first question is then, hi, where is Mountain Pleasant? I don't see any mountains here. I thought it's a Mountain Pleasant. So anyway, so so if you look at this flow energy, the density should be constant before and after, and the pressure should be constant before and after. So you can neglect the change in flow energy. Because when you write Mount Pleasant, some people prefer MT. MT sounds like mountain, isn't it? MT Everest, MT Pleasant. So I was expecting a tall mountain because I was from Texas. There's no mountain there. So I was expecting, oh, there's the mountain and much better weather than there. Apparently, there's no mountain here. So the next one, the kinetic energy. Is there kinetic energy change? Yes, there is, because the velocity is 3 meters per second. The velocity of the lake. What is the velocity of a lake? 0. So there is no velocity. So there is kinetic energy change. What about potential energy? There is a potential energy change. Look at that, 90 meters. So we need to consider kinetic energy change and potential energy change, an upgrade from the previous problem, right? Okay. So let's look at this one. The kinetic energy first. How can you determine that? It's simple. Velocity square divided by 2. What is the velocity? 3 meter per second square divided by 2. What about the change in potential energy? Gravity times elevation. 9.8 meter per second square times 90 meters. So if you do, you get the specific mechanical energy. The answer is 887. 887. What is the unit? Meter square per second square. Meter square per second square. So you are going to write meter square per second square here. Not anymore, because we know how to do a dimensional homogeneity. We learned that this one is the same as joule per kilogram. So I'm going to write joule per kilogram, which is the same as meter square per second square. So that is the specific mechanical energy. Then let's calculate the power generation potential. How do you do that? First, power. Power is energy divided by time. So the energy is going to be mass times specific mechanical energy, this one, over time. What is m over t? Mountain? No. That was a joke. Didn't work. Imagine that you are trying to make a joke in your secondary language. Not easy, right? But I'm doing my best. M dot times E. There was only one joke worked, from my mouth in the last 10 years. The conservation of energy principle, 3 hamburgers and poops and remaining. So how do you determine m dot? There are 2 different ways. One is density times volumetric flow rate, or density times average velocity times cross-sectional area. So which one we are going to use? In this case, we know the volumetric flow rate, so I'm going to choose this one. So that is density. Is density given? Oh, the density is not given. So what do we do? Just give up? What is the density? You all know that. What is the density? What? Atmosphere? No. What is the system here? Is the system air or water? Water. What is the density of water? Yes. Technically, the density of water changes with respect to temperature. However, the change is extremely small, so we assume it to be incompressible. Incompressible, right? Yeah. So that is 1,000 kilogram per cubic meters times volumetric flow rate 500 cubic meters per second times specific mechanical energy 887 joule per kilogram So kilogram, cubic meters. So we get approximately 444 mega joule per second watt. So that's how you solve this problem. Any question? What time is it? Oh, we have 12 minutes. You know, that's plenty of time. I can drive my house and then, you know, cook my lunch and then come back and continue. No? The thing I like about this town is it takes about 2 minutes drive to my house. When I was in University of Texas, it took about 1 hour 30 minutes to get to the campus. When the outside temperature is 117 Fahrenheit. Imagine that your air conditioner was broken. One day the air conditioner was broken. And it was after my class. So it was at 4 p.m. Really hot. My car was outside in the parking lot. There was no garage. I don't know why they don't use garage there. And it was hot. And I had to drive 1 hour 30 minutes to get to my home. Then I decide, okay, let's move to Michigan. Okay, so that completes kinetic energy and potential energy. So if I ask, you know, how to determine kinetic energy, potential energy, and power generation potential, now you can do that, right? Energy transfer by heat. This makes thermodynamics. When you have a thermodynamics problem, there is an energy transfer. There are two energy transfers. One is heat transfer. The other one is energy transfer by work. But there is something very interesting, something you like in energy transfer by heat. When you study transfer in dynamics class or, you know, the solid mechanics or any other classes in this building, when there's a transfer, when there's a movement from one location to the other location, what you need to study? Vector, right? This much value in this direction, right? You like vector? You do. No, we don't, right? In heat transfer, we don't worry about X, Y, Z, R, theta, Z. We don't care about the direction of heat transfer because heat transfer direction is already determined by what? The second law of thermodynamics. So if I have a hot coffee, heat transfer direction is, we don't need to worry about X, Y, Z coordinate system because heat transfer direction is going to be everywhere. So we don't study vector. Isn't that sounds good? No? Okay. So let's talk about heat transfer. Heat is the form of energy that is transferred between two systems or a system and its surroundings. What we are going to study is heat transfer between a system and its surroundings. Okay? And when there's a heat transfer, means that there is temperature difference from higher temperature point to a lower temperature point. When you touch something, you feel that it is cold. That means that this one is at lower temperature than your body. When you touch something, it is hot. That means that that one is at higher temperature than your skin. What about if you touch something that has the same temperature as your body temperature? Then there is no heat transfer. So you don't feel it is hot or cold. If you feel it is hot or cold, meaning is that there is a heat transfer. To have a heat transfer, one should be at higher temperature than the other. Okay? So when I say there is a heat transfer from here to the outside, so there's a heat transfer. By the way, when we say heat transfer, we use this letter Q to represent heat transfer. So when I say there is a heat transfer Q out from this system to the outside, can there be heat transfer in, Q in? So if there is a heat Q out, there can be Q in? It's a question. So you have a 50% chance to be right. It's going to be yes or no. If there is a heat transfer, Q out, is there Q in? No, it is not possible, because when you say there is a Q out, meaning is that the system is at higher temperature than its surroundings. So there's only Q out. When you hear that there's a Q in, then meaning is that the surrounding is at higher temperature than the system, so there is no Q out. Okay? Not much thing that I can discuss. Well, one thing is that adiabatic system. Adiabatic system means we have plenty of insulation. So if you can neglect heat transfer, then you say this is an adiabatic system. It's a theoretical system that doesn't allow any heat transfer. We use this term a lot, adiabatic system, in thermodynamics. So you may want to remember it, okay? So that's everything about energy transfer by heat. The details of energy transfer by heat, if you want to study that, you need to go to EGR356, heat transfer. And who are you going to see? Me again, okay? Then there are two energy transfers. One is by heat and the other one is by work. The one is the energy transfer associated with a force acting through a distance. Force times distance is work. And there are many different, the work can be piston work, shaft work, electric wire work, and etc., etc. But, since we are studying thermodynamics, not them. So we will, simplify this, and we will only use electric work in this course. Okay. One thing very important is that the formal sign convention. We assume that heat transfer to a system from its surrounding is positive. Sounds like energy transfer by work into a system is positive. Mathematically sounds right. However, in thermodynamics, we assume that energy transfer by work done by the system to the surrounding is positive. We are going to talk about this later, but this is very important. Formal sign convention. So it's like, the plus minus when you have a battery system. It sounds like, the electrons come out from, the positive, but it comes out from negative, right? So there's a, the mistake, from people long time ago. Same mistake from long time ago. So when we talk about energy transfer, later when we, use energy balance equation, we are going to do that, I think next Tuesday, when we talk about energy balance equation, when you have a system, when there's a heat transfer in, Q in, and heat transfer out, Q out, and there can be also energy transfer by work goes in, energy transfer by work comes out. This one is positive, and not this one. This one is positive. This one is negative. This one is negative. Okay. So don't forget that. And when you go to next Tuesday, when we study energy balance equation, we are going to discuss how to deal with this. Okay. These are just very simple, that you can just read through. And what the important thing is going to be on this slide. Then how can we determine energy transfer by work? There are many different ways. What we are going to use most in thermodynamics is electrical work. And electrical work can be determined by voltage times current times time. If you want to determine electrical power, you divide this electrical work by time t. So it's going to be voltage times current. The unit is going to be watt and joule. The rest is just for your reference. Okay. So you may use them in your homework assignments, but we don't use them in our classroom or your exam. Okay. So that's everything about energy transfer by heat and work. From next week, we are going to study energy balance equation. Okay. Any question about today's lecture? No. Then see you next week. Thank you.